All right, so 9 o'clock, we'll get going. Thanks everybody for joining and giving us an hour of your time. Really look forward to this one. I had a good run through a couple days ago with Doug, Richard, and Kevin, and really excited to be able to share this their knowledge. So I'm going to stop talking right away and hand it over to Kevin to take us through the introduction and onto the content. So thanks, guys.
Excellent. Thanks, Braden. Thank you, everyone, for joining us today. I'd like to get things started off with a safety minute to talk about the current conditions around us in the winter regions of North America. As springtime is setting upon us, we're getting to the warming and cooling through the night and the day. So be aware there's slippery road conditions, slippery parking lots. Be cautious, be gentle with your movements if you're driving to ensure that you don't end up in some kind of incident. Just a little bit of housekeeping here. Feel free to ask questions throughout the presentation. They can be answered online or we can provide verbal answers if need be. We'll have a little bit of a Q&A session at the end as well. But the Q&A button on your ribbon, the Zoom ribbon, will be the location where you can place questions to the panelists, to the hosts of today's presentation. So moving on to about CGIS. We track or trace our roots back to 1965. CGIS was officially founded in 1980 as we took over the ownership of a valve division from our sister company that was founded in 1965. And throughout the many years of our experience, we've developed various streamlines in our business to support our customer base throughout the world. Primarily based in Canada, but we have operations around the world. We've developed the engineered solutions primarily to focus on severe service, critical applications for every industry that runs process as their main part of their business. Streamlined solutions for day-to-day utility needs in the world of valves. Obviously project solutions and service to be able to support our partners, whether that's on the end user level or the manufacturing level. Chaoda, privately held since 1984. They are focused on the infrastructure and technical development. They own the entire supply chain process right from the foundry to manufacturing, to boxing up and shipping it to our customers. 1.5 million square feet in manufacturing area. And of note, they have a complete North American team on quality control for the North American marketplace. So our presenters today are Doug Jones, Richard Harmon, and myself, Kevin Niebergall. Doug Jones has 38 years of experience with a focus on severe service. He's the Vice President of Sales and Marketing with Chaoda USA and serves on API committees and task forces, including API 641 for fugitive emissions. Richard Harmon is also based out of Houston, Texas. He's the Director of Marketing at Chaoda, and he has 10 plus years in the industry in various sales, marketing, product management roles. Myself, I have 26 plus years of experience in primarily Western Canada, focusing on oil and gas, pulp and paper, and LNG or cryogenic services in the oil and gas marketplace. I'm based in Prince George, BC, Canada, and on to the next. So I just wanted to touch on valve selection approach. We believe that the application always dictates the valve. We see different conditions presented to us in many different processes that affects material selection, design selection, and there's a few that we need to consider in the oil and gas market, liquid or liquids, the gas, corrosion or chemical attack that we'll find with acid gas applications, the presence of chlorides, percentages of H2S, CO2, and H2O. So we need to factor that in, not only to what metal do we use, but what are the components that seal those various metal components to protect against external or internal leakage. So we always start with the application and then consider what valve options we would have. So as part of my portion of the presentation, I'm going to talk about some of the applications that we'll commonly find in the oil and gas industry or in pipelines, to talk about some of the different designs or setups, and then allow Richard and Doug to dive into the technical differences in the types of valves. So common, we'll find Trunnion mounted ball valves, or DBB and DIB, on line breaks to protect the piping system or the environment. It's monitoring the upstream, downstream pressure conditions, is a fully closed loop, self-contained system that will react based on the pressure conditions of the piping system in the event of a break or rupture of a piping system. Pigging valves. Doug will share with us some innovation in the pigging valve or the pigging valve operations later in the presentation. But this is our conventional setup for launching or receiving pigs, whether they're a smart pig or a cleaning pig. And we can see that there's numerous valves around this system, various conditions where isolation is extremely important because we are opening this valve to the atmosphere area where it's installed. So we have a mixture of, normally we'll see mostly manual valves here. The automated valves are primarily part of the pipeline. So you can see that we have a manifold, receiving barrel that's connecting to the main line. So for what's the purpose of pigging? Cleaning to remove any liquid or sediment or anything that has developed within the piping system that could potentially lead to corrosion or is affecting the volume of flow that's able to go through the pipeline. The integrity has become extremely important over the last number of years. Introduction of smart pigs to measure wall thickness, identify any cracks, and corrosion issues that may be occurring within the piping system so that we can do a far better job of maintaining the safety of that pipeline. Underground valves, not the common for us in day-to-day business, but underground valves. This is an example of an underground valve that has a fully welded body to prevent any type of migration of media into the valve from external contaminants. Lines are running up from that valve so that we're able to inject sealants or lubricants to assist the valve in its performance. And then that is buried below ground so that we're below the freezing points so that we can safely operate. In general, this is going to be my handoff to Richard. In the world of Trunnion mounted ball valves, there's a common misunderstanding of what is double block and bleed, what is double isolation and bleed, because as we look at this valve on the left side of the screen, that is a DIB1 valve, but you can't tell that. It's hidden within the walls of the valve, and it becomes clear to understand how that valve is set up and what the differences are between the DBB or the DIB 1 and or 2. So on that note, I will pass it off to you, Richard.
Thanks, Kevin. Can you all hear me okay? Okay. Yeah, so, just from kind of what Kevin, introduced, I wanted to take a little bit of time and talk about pipeline isolation and how it interacts with valves. It's a topic that gets talked about a lot, and there is some confusion because not due to anybody's fault, but because there's a lot of competing and conflicting terminologies and philosophies about pipeline isolation. So I hope that what we could do is run through some of these definitions, run through some of these scenarios and design principles with respect to valves, so that everyone can kind of have a better understanding of what the different definitions are, and then have an idea of what type of questions that you need to ask to get a good understanding of how a valve performs in pipeline isolation. So, if we can accomplish that in this webinar, like, we'll be doing great. So, with respect to pipeline isolation, obviously, it's a critical facet of safety in pipeline work, right? For a pipeline that's been constructed and now needs to be maintained, being able to reliably and safely isolate sections of that pipeline so that you can work on them or clean them or do whatever you need to do with them, being able to do that safely is absolutely key. And all of the different players recognize that. So when you're talking about isolation, where you start to get a little confusion is that there are different players involved in kind of defining like what is truly safe and what is best practice for isolating a pipeline for maintenance, for example. So I list out a few of these on this slide. You've got government agencies, right? Which have so you have both sort of national government entities and then also provincial entities that each have, some say or some sort of philosophy about best practices for pipeline isolation. So you've got government agencies, you've got standards groups, for example, API, the American Petroleum Institute, that put forward definitions or philosophies of certain aspects of pipeline isolation. And then the third big group is that you've got pipeline operators themselves, who often write their own work procedures, work instructions, and that type of document with respect to proper pipeline isolation for work. So all of these three are together putting out sort of definitions into the world, and it's important to kind of understand generally how they interact. And then the other big piece of it that we'll go through is different valve types, kind of to Kevin's point, different valve types and different designs of valves behave differently. And it's important to have some understanding and clarity on that so that you can understand how that valve is expected to perform in an isolating service in a pipeline, in an isolating application. You want to hit the next slide? Okay, so the operators, the pipeline operators almost always have their own specific standards for pipeline isolation. It's usually a separate document that is a work instruction or a standard of some kind. Procedures are to reliably isolate a pipeline segment and go in and do work on it. So I put a little picture in here of one from ConocoPhillips in Canada. They've got their own, but virtually everyone else I'm aware of also has their own as well. If you're if you're dealing with these companies and you don't know what in specifically what their isolation procedures are, it can be very helpful to just ask for that information, because in order to correctly specify valves for some of these pipeline operators, you really need to understand what their isolation philosophy is. So that's all you really need to kind of take from this slide. If you want to go to the next slide, Kevin. Government, with respect to government agencies, this varies by country. It's a little different in the US than it is in Canada, from what I can tell. And I'm certainly not an expert on Canadian law by any means. But just from kind of a general review, in Canada, there is not really an overarching or an all-encompassing definition about valve isolation in pipelines. But there are safety regulations with respect to pipeline isolation that are, generally speaking, happen at the provincial level. So it's an important thing to be aware of, is that these things can vary by province, and you need to understand that. I think, thankfully, in the case of a lot of the pipeline operators, especially those that operate nationwide, they will probably make some reference to provincial regulation in their pipeline isolation standard, right? So that that specification will go through and say, in British Columbia, you need to do this when you're isolating the pipeline. Somebody needs to be there watching the bleed valve and making sure that it doesn't, expel media, for example. So something to be aware of. Things can change between provinces, and you want to make sure you're kind of just generally aware of that. So next slide, Kevin. Okay, and then the last group that we kind of talked about was the standards groups. The big one here with respect to pipelines is really API, the American Petroleum Institute. They have put forward a specification that many people are familiar with. It's really integral to pipeline operations all over North America, and that is API 6D, which is a specification for valves for pipeline service. And in the last few revisions of API 6D, it's revised about every 5 years by a dedicated task group. And in the last few revisions, they've been sort of putting forward some more clear parameters about valve performance in various isolating operating scenarios. And they've developed some terminology with respect to that that's a little bit more standardized, that I think gives everyone, if you understand it, a good basis for having a common language, speaking a common language with respect to how valves function in different operating scenarios. So as we go through some of the technical details, I'm going to be pulling out definitions from API 6D and giving some, explanation to those, so that you can kind of understand that, at least from API's perspective, here are some of the common definitions, and here's how they match up with valve function. So we'll go through that. You want to? Okay, so this slide, so we're going to just get into the first kind of thing we're going to talk about is double block and bleed. Double block and bleed is a phrase that's been out there forever and a day, but there are kind of conflicting definitions, or competing, I should say, definitions of what is double block and bleed, what should it do, and what do you need to accomplish it. So with respect to that, generally speaking, there are kind of two generally accepted definitions. There's one that's been put forward by the American Osha, and then there is a definition of double block and bleed that's been put forward by API 6D, or the American Petroleum Institute in general. So we'll dig into those and kind of understand what the difference is and why it matters a little bit. You want to go to the next one? Yeah. Okay, so for Osha, so this definition on the slide as read is the exact definition of what Osha considers a double block and bleed configuration. They define it as the closure of a line, duct, or pipe by closing and locking or tagging two inline valves, that's two valves, and by opening and locking or tagging the drain or vent valve in the line between the two closed valves. So in the illustration, you can clearly see you've got two valves there in series, and in between them, if you look at the little blind, at the little spool in between them, you can see there's a little bleeder at the bottom of it, right? And that's one of the critical key functions of being able to perform, you know, a double block and bleed configuration per OSHA, is that you need to be able to, number one, have two valves installed in line. Number two, close both of those valves. Number three, you open your drain valve. And so what does that do for you? It allows you to visually verify that the sealing integrity of that double block and bleed assembly is there. So the idea of having two valves in line is, think of it like an insurance policy, right? You've got one valve on the upstream side that's that primary seal in that pipeline, right? It's performing the isolation in an ideal scenario, and you're able to verify that with your drain valve. If it starts to not seal anymore, you're going to start to see media coming out of that drain valve. And then you still have a second valve downstream of that spool piece that is still providing a backup secondary isolation. So that's, you know, this is basically all about pipeline safety, and this is what OSHA defines as a double block and bleed assembly that that you can put in a pipeline and assure that you can isolate that downstream segment of the pipeline safely and have a means of verifying that you've done that. So that's OSHA. API 6D has a little bit of a different definition and a little bit of a different philosophy. So this little paragraph right here, brief couple of sentences, is the exact API 6D definition. They define double block and bleed as a valve with two or more seating surfaces that in the closed position provides a seal against pressure from both ends of the valve with a means of venting or bleeding the cavity between the seating surfaces. I put an illustration in here to show you, so double block and bleed for API 6D is specified essentially as a test to be performed to a single valve that assures that you can use that valve to not just isolate your media, but also verify that you are isolating it, right? So the test procedure is, if you look at the illustration, you're applying pressure against both sides of the valve at the same time, and the valve is in the closed position. And then once you've applied that pressure against both sides, your valve should have a small drain valve, or it can be a vent valve, but usually it's a drain valve. You have a small drain valve attached to that valve that's connected to the body cavity. And the body cavity should be isolated from the pressure that you're applying on both sides, so that you can open that drain valve up, and you should be able to visually verify that that valve is sealing against the pressure from both sides at the same time. So you can open that valve up and you should not see any media coming out of there. If you do see media coming out of there, that is a problem. So that is the API 6D definition of double block and bleed. And when you compare OSHA to API 6D, the immediate question that sort of comes up, or the immediate thing you notice, is that OSHA requires two valves. You have to have two valves to meet the OSHA definition. Whereas with an API 6D definition of double block and bleed, a typical trunnion ball valve and other types of valves as well can meet that definition of double block and bleed with just one valve. So that's one of the kind of crucial differences. So from double block and bleed, we've kind of talked about that. I think, you know, we kind of understand the key differences. From there, we're going to kind of move into some a little bit more challenging definitions of pipeline isolation. And I want to start with really like the valve design fundamentals. it's if you want to understand how, for example, the concept or philosophy of double isolation and bleed works, you really need to understand a little bit about how a valve seat works and how valves can be configured to provide isolation. So we're going to talk a little bit about seat design terminology and to kind of ground ourselves in like how a valve works and have a shared kind of definition of that so that we can move forward to understanding how that valve with those seats works in a pipeline. So we can kind of cover three general definitions here. These are all definitions provided to us by API 6D, and the terminology is as well. And these three are kind of the key three ones to understand if you want to kind of understand pipeline isolation. So 3 seat types or definitions. The first one is what API 6D refers to as a unidirectional seat. I typically, in shorthand, call it a one-way seat. You'll also hear it referred to as a single piston effect seat sometimes. The core idea behind this is a seat that is designed to seal against a pressure source in one direction only. So that seat is set up so that if you're applying pressure from one side, you will get a positive isolation. And if it goes the other direction, you will not get a positive isolation. So that is a unidirectional or one-way seat. The second seat type we're kind of going over is what they call, API 6D calls it a bidirectional seat. I typically call it a two-way seat. You will also hear it referred to as double piston effect by some valve manufacturers. This type of seat is a seat that's designed to seal from a pressure source in either direction. One way or the other, it doesn't matter. That seat is designed mechanically and has O-rings configured in such a way that it's going to positively seal no matter which way you're applying pressure, right? So that's a bidirectional or a two-way seat. Now, I want to be clear about unidirectional, bidirectional with respect to seats. Like I said, these are the terms that API 6D gives us. A unidirectional seat or a bidirectional seat does not have anything to do with the valve directionality, okay? So you can have a valve with unidirectional seats and the valve is bidirectional, okay? So when we say unidirectional or bidirectional with respect to a seat, all we're talking about is how the seat behaves when you apply pressure to it. If the seat seals pressure in one direction only, then it's a unidirectional seat, can go in a bidirectional valve. That happens literally every day. If the seat is able to seal pressure sources in two different directions, that is a bidirectional valve, a bidirectional seat, and actually you could theoretically put that in a unidirectional valve. So just be clear, and I will from here on out probably refer to them more often as one-way seats or two-way seats, and just understand that these seats don't necessarily have anything to do with the directionality of the valve. So that's one-way seats and two-way seats. The third kind of definition that we'll talk about is self-relieving seat configurations. When we refer to self-relieving seats, what we're talking about is how the seat behaves when there's body cavity pressure that's built up in excess of the line pressure. It's an important topic with safety, with respect to safety and pipeline isolation. It's often maybe not given as much attention as it should be, because when body cavity pressure is allowed to build up without a means to relieve it into the line or somewhere, what you've got is you've turned a valve into a pretty dangerous piece of hardware, right? So it's important to consider valve design, to consider seat design, to ensure that whatever valve you're installing, there is some means of relieving body cavity over pressure when the valve is in a closed position. If you don't, it can be a dangerous thing. Typically, it's not uncommon for trunnion ball valves, for example, to have self-relieving seats as a standard, and they relieve body cavity overpressure to the line automatically, and you don't have to worry about it. But as we get into some of the other seat configurations, some of them do not do that. And so you need to make other provision. Typically, what that would be is an automatic vent valve, for example, set at a certain set pressure that'll automatically relieve the body cavity overpressure at a certain PSI. Or they'll also have more complex piping systems you can install on the valve body that automatically relieves that overpressure to the upstream or the downstream side, depending on what the user wants. So those are the basic kind of seat terminologies we need to understand so that we can go through some of these valve configurations. Okay. So we're going to talk about self-relieving seats first, and this is this configuration. I will tell you, this is a pretty common configuration for trunnion ball valves, API 6D trunnion ball valves. Okay, most manufacturers have a self-relieving seat design as their standard seat design, and there's a reason for that. It makes things a lot simpler if you don't need like a double positive isolation. So the definition of a self-relieving seat design is that the valve seat is designed to relieve pressure in the valve body cavity. So it's also important to note that if you're talking about self-relieving seats, depending on the valve type, be it a trunnion ball valve or a slab gate or any other type of valve like a plug valve, configurations that relieve body cavity pressure can either relieve them to the low pressure side of the valve or the high pressure side of the valve. And so if that matters to you, oftentimes I find that it doesn't really matter to users that much, but if that matters to you, it's something to consider. So we're going to kind of go through in this illustration what it looks like, and this is what we're kind of considering as our example, which is a kind of standard vanilla trunnion ball valve that's got two one-way seats installed into it. So if you look at the illustration, we've got pressure coming from one side of the piping only, or high pressure coming from one side of the piping only. It's going against that upstream seat. And like we said earlier in the terminology definition, that one-way seat, that's designed to seal pressure from one direction only, right? So what's happening is you've installed a one-way seat on the upstream seat, and that seat is providing a positive isolation against the pressure source in that direction. And then on the downstream seat, you're getting pressure in the body cavity core, right? And that pressure, we're saying that is equal, that is higher than the downstream pressure, right? Because it's in an isolating application. So when that pressure in the body cavity exceeds the downstream pressure, that one-way seat, because it's only designed to seal in that one direction, that downstream seat is relieving the body cavity overpressure, okay? And that happens automatically. There's nothing that needs to be done. There's no switch that needs to be flipped. There's nothing that needs to be, opened up. That happens automatically. So this trunnion ball valve that is installed with two one-way seats in this configuration is what most manufacturers would refer to as like a self-relieving configuration. Self-relieving seats, it's the most common seating configuration that most trunnion ball valves have. It deals with body cavity overpressure automatically, and it relieves it typically to the low pressure side, and you've got one source of positive isolation from your upstream seat. So that's how this valve works. You want to hit the next? There you go. Okay. Okay, so the next kind of configuration we're going to talk about is two-way seats installed, right? So going back to our Bi-directional seat configuration that we talked about, those two-way seats are designed to seal against pressure sources in either direction. Doesn't matter for them. They'll seal it either way. So in this scenario, we've got pressure being applied from the upstream side, and you're getting positive isolation on that upstream seat. But you are also getting positive isolation on the downstream seat. So for example, if you have body cavity overpressure, that downstream seat will not relieve it, right? Because it's providing isolation against the pressure. It doesn't care whether the pressure is coming from the body cavity, whether the pressure is coming from the piping, it doesn't matter. It's going to seal no matter what. And so what that means, so there's a benefit to having two-way seats installed. That benefit is that you're getting two seats that are both doing the work of positive isolation. So for example, if you have pressure in one direction hitting that first seat, and say there was some crud or garbage or whatever that flowed down the line and damaged that upstream seat, and that upstream seat failed, you would still have positive isolation on the downstream seat. It would seal that valve. That's the upside. The downside to having two bidirectional seats installed like this is that body cavity overpressure, like I said, will not be automatically relieved. It will sit there and build up unless you make a specific provision in the valve configuration to relieve that body cavity overpressure. Typically, like I said, that is a vent valve with a set at 300 psi or 1500 psi or whatever it may be, depending on the valve pressure class or the pipeline pressure, and it can also be like a more sophisticated kind of piping system. So that's what it looks like with two bidirectional seats installed. So again, just to reiterate, we went through a little bit of how you can kind of configure unidirectional one-way seat, seals pressure sources in one direction. Bidirectional or two-way seats gets the pressure source in either direction and seals it, isolates it. And then self-relieving, which most often for most ball valve manufacturers, their one-way seat is designed as a self-relieving seat. So you can, those two terms are not interchangeable, but most of the time, most manufacturers, you get a one-way seat, it's a self-relieving seat. So that's the terminology. I'm gonna hit the next one. Okay, so let's talk about API 6D and their definitions of different types of valve isolation. So we're going to talk about double isolation and bleed. How is double isolation and bleed different than double block and bleed? The API 6D definition of double isolation and bleed, or DIB, is that a DIB valve is a valve with two or more seating surfaces, each of which, so each seat in the closed position, provides a seal against pressure from a single source with a means of venting or bleeding the cavity between the surfaces. So in the API 6D definition, you have a double block and bleed. You just have to be able to seal when you apply the pressure in both directions at the same time, right? Double isolation and bleed requires that those seats positively seal both of the seats positively seal against a single source of pressure. When we were talking about a scenario of a valve installed with two-way seats, that valve would meet the requirements of double isolation and bleed. Why? Because if you apply pressure from one direction, you're going to get positive isolation on the upstream seat. And if anything were to ever happen to that upstream seat, you would still get positive isolation from the downstream seat. So that is the definition of double isolation and bleed. You have to be able to seal against a single source of pressure on both of your seats, not just one. So In API 6D, they call out two different ways that you can achieve this. They refer to them as DIB1 and DIB2. DIB1 is with a trunnion ball valve. DIB1 is achieved with having two bidirectional seats, exactly like what we were talking about just on the last slide, right? You put two-way seats in there. They seal against pressure from either direction. You've got double positive isolation in either direction. It doesn't matter. So that's DIB1. That is the most common specification for a double isolation and bleed valve is DIB1. They want two-way seats installed. Those two-way seats will isolate pressure in either direction. You're golden. You have double positive isolation in one valve, and the only downside you have is that you need to figure out what to do with your body cavity overpressure. So that's the most common double isolation and bleed technology. There is another one in API 6D they refer to as DIB2. DIB2 is use one two-way seat and one unidirectional seat, one-way seat, okay? And what that does is it allows you to achieve double positive isolation only in a certain installation direction. So like, let's think through this a little bit. So the illustration we have here, we've got a trunnion ball valve with one-way seat and one two-way seat, okay? And the way that we have it installed, the pressure is coming on the upstream side and it is hitting that one-way seat. Well, what do we know about one-way seats? A one-way seat seals against pressure in one direction only, right? And the two-way seat seals against pressure in either direction. So if you have your DIB2 valve, which we defined a DIB2 valve as having one-way, one two-way seat, if you've got that valve installed in the direction like we have illustrated here, where the pressure is coming from upstream, it's hitting that one-way seat, and what's it do? It's providing positive isolation on that one-way seat. If that one-way seat were to become damaged by a rock flowing through the pipeline, I've seen it happen before, or something like that, and that one-way seat were not able to seal anymore, what do you have? You've got a two-way seat downstream, right? And what do we know about two-way seats? They seal against pressure in any direction. They don't care, right? So that if you lose your capability to isolate on that one-way seat, you've still got your backup two-way seat that is going to provide you with isolation, okay? So that DIB2 is able to, that DIB2 configuration is able to give you double positive isolation exactly like a DIB1. What is the difference? Okay, if you flip this valve around and you've got the two-way seat on the upstream side and the one-way seat on the downstream side, you will not get double positive isolation. Your two-way seat on the upstream side will seal. But if it were to fail, your one-way seat on the downstream side would relieve. Like it would not seal. It would perform essentially like a traditional self-relieving seat trunnion ball valve. So you would not get the double positive isolation. So DIB2, just high level, the easiest way to think about it is it's got one two-way seat, one-way seat, and it's able to give you the same double positive isolation as a DIB1, but only if the bidirectional seat is downstream. So the way that I like to think about it is DIB2 is like the best of both worlds, right? So the last thing about DIB2 is that you've got, if you have, so when talking about body cavity overpressure, you've got a one-way self-relieving seat in your DIB2 configuration, okay? And what that means is that if you have this valve installed the way we've got it illustrated here, with a one-way seat on the upstream side and you've got pressure coming against that, if you have any body cavity overpressure in that valve, that overpressure will be automatically relieved to the upstream side because you've got a self-relieving seat in there. And so with a DIB2 valve, you can take care of body cavity overpressure without having to have a vent valve, without having to have external piping or anything like that. The only downside to a DIB2 configuration is you need to have it installed with the pressure coming from one direction so that you can make sure that the bidirectional seat is always downstream. So yeah, I think that's good on that slide. Okay, so we've kind of gone through the seat design, the seat features or the seat designs that you can have. We've gone through the definitions of double block and bleed and double isolation and bleed, both DIB1 and DIB2. And I wanted to provide just kind of a general overview because we really talked about, I tried to provide y'all with sort of illustrations from Trunnion ball valve land. And so I want to talk about a little bit more about different valve configurations and how they sort of stack up with respect to their sealing technology and their ability to achieve either double block and bleed or a double isolation and bleed configuration. So if we go through what we talked about kind of in order, you know, your two valves with a bleeder in between, the sort of Osha configuration that we discussed, which is a pretty simple setup. It can be achieved with basically any valve. You could put two floaters in line, floating ball valves in line. You could put two gate valves in line. You could put two globe valves in line with that bleed valve in between, and you'd be able to achieve both double block and bleed and double isolation and bleed with that configuration. The only problem is it's two valves. It's, you know, it's a little bit of extra more length than you know, your trunnion ball valve or other types of pipeline valves that can achieve the same thing in a smaller footprint. So that's your two valves with a bleed in between. Your typical trunnion ball valve, which, like I said, most trunnion ball valves and most manufacturers standard is a self-relieving seat configuration. So their sealing is upstream sealing, it's pressure energized, and it's typically self-relieving. Most trunnion ball valve manufacturers that supply that style those valves are typically double block and bleed capable. It does depend on it does depend a little bit on the trunnion ball valve design. Okay, so it's possible to design a trunnion ball valve that isn't double block and bleed capable. So if you are in doubt, ask the manufacturer. So they typically are double block and bleed capable. They are never double isolation and bleed capable for that type of self-relieving seated trunnion ball valve. So when you go down, you get to a DIB1 configuration. If you're, you know, so that's a sealing configuration that provides both upstream and downstream sealing. And it's typically achieved with having two-way seats or bidirectional seats installed in it. Those valves are typically double block and bleed capable, and they are also double isolation and bleed capable, right? Because they've got two-way seats. They isolate pressure in either direction. They don't care. So that's your DIB1 trunnion ball valve. Your DIB2 trunnion ball valve, they do upstream and downstream sealing, and they typically, like we said, have one-way seat and then one two-way seat. So one bidirectional, one unidirectional. Those are also typically double block and bleed capable. They are double isolation and bleed capable, but only if the bidirectional seat is downstream. So it's important to note that. But if your pressure in your pipeline is only ever coming from one direction, DIB2 is an awesome option for you because you can get away with having that valve that provides you with that double positive isolation, and you don't have to worry about dealing with your body cavity overpressure. So that's a DIB2. Floating ball valves are a pressure energized seat design. We won't get too into it, but suffice it to say that floating ball valves are not double block and bleed or double isolation and bleed capable in their typical configuration. Slab gates or through conduit gate valves are typically pressure energized. I want to note that with slab gates and with expanding gates, there's a little bit more variation between different manufacturer designs than there is with trunnion ball valves. And so like I would caution you to, if it's not clear what the manufacturer is selling you or speccing to you, ask the question, because there is a little bit more variation between different manufacturers' designs. But typically speaking, slab gates, as defined with the sealing mechanism defined in API 6D, which is that they're pressure energized and they have fixed seats. That style of slab gate is typically neither double block and bleed nor double isolation and bleed capable. However, I know for a fact that there are slab gates out there that are capable of doing a double block and bleed. Double isolation and bleed is typically not possible for a slab gate. A DIB1 style through conduit is a much different type of design, and those valves can be capable of both double block and bleed and double isolation and bleed. But that's a little bit of a different animal. So you definitely want to, if you don't just expect to be able to get a DIB1 slab gate, if you want it, you really need to specify it. And then expanding gates are a totally different animal. They're typically not pressure energized, they're mechanically energized. So the sealing mechanism of an expanding gate is the mechanical energization of the gate and the segment inside of that valve. And so they are both double block and bleed capable and DIB capable, and typically not able to be supplied in any kind of self-relieving configuration. And therefore it's very common that when you see expanding gates out there in the field, they will almost always come with a piping configuration that can relieve the body cavity overpressure to the upstream side of the valve, because there's just no way to make a expanding gate that can have self-relieving seats. So that kind of gives you an idea of what some of the different typical pipeline, valves used in pipeline applications and what they can do. Typically, I always try to emphasize, like, some of these details are dependent on the manufacturer's specific design. And so if you have any doubt, you should ask. So the key takeaways here is really high level. I hope that this was helpful, at least in helping people think through the issues that are involved in thinking about pipeline isolation. The important thing is not necessarily to have all this information memorized, but more so to kind of know what type of questions to ask and know what the factors are in play, right? So one of the first things you want is you want to understand what you need your valve to do, right? To meet the regulatory requirement you're under. So if you have a clear understanding of what you need that valve to do, you can typically kind of translate that either into a clear API 6D approved definition of, hey, I need a DIB1 or I need a DIB2 or I need a double block and bleed, but also be able to kind of get that, clearly from the manufacturer. The second piece is be clear on what terminology is being used. If you're hearing something from someone and they're telling you about double block and bleed, right? As we were talked about, there's competing definitions of double block and bleed. So if somebody tells you about DBB, make sure that you understand where their head is at, where they're coming from with respect to that definition. Are they talking about an Osha definition, or are they talking about the API 6D definition? And then the third thing is, having some understanding of how your valves behave in different operating scenarios. So that all comes down to essentially, with respect to isolation, that comes down to the seating technology. If you've got a good understanding of how that works, then you can kind of work your way through to the solution of what you're trying to achieve. So I think that's about all I got. Doug?
Thanks, Richard. I think it's certainly a pertinent topic to everybody that's on here, and there have been some good questions, right? So tried to answer a few. There's a few left open. So kind of as we go through here, if you can handle some, and then we can leave the others to the end. So, you know, what Richard just talked about was a lot about pipeline safety. You know, we're going to kind of transition a little bit, since this is a safety webinar, and now we're going to transition a little bit into something more related to personnel safety, right? So, and this is about the methods, the various methods of pigging operations within a pipeline itself, and really to talk about some alternatives to the traditional pig launching and pig receiving operations that have been historically associated with pipelines. So the picture on the left is really just kind of a photograph of a traditional barrel style pig launching and isolation system. It's basically a barrel style launcher where the pig is inserted. Then there are isolation valves, you know, kind of after to in order to isolate the pig. That also plays back to Kevin's schematic that he put up in earlier times. More recently, you know, there have been pigging alternatives to the traditional barrel style, where the pigging itself can actually be accomplished within a single valve. It's essentially a Trunnion ball valve format platform that also incorporates closure, a closure style that will allow access to the valve cavity, and then what has been termed the pig bar in the earlier schematic is then accomplished with a catcher plate that's internal to the valve. So it's generally used in, I'll just say, shorter pigging operations, shorter pig runs, smaller diameter pipelines, maybe up to 16 or 20 inch in size. Certainly the advantage of the pigging ball valve is the fact that it's a much smaller footprint, as is obvious in that picture, than what so the environmental impact is a little bit less than what a barrel style launcher might do. Also the fewer number of actual joints, right? So body joints, pipeline connections, flange joints, all that sort of thing. So it's a lower fugitive emissions option, much more efficient operation, more effective to install and maintain. And then you know, this is going to be very brand specific, so I apologize in advance. But you know, Chaoda is one of the more recent entrants into the valve pig valve category, and as a result of that, sometimes one of the advantages of being one of the later ones into the game is that you get to observe some of the weaknesses or some of the deficiencies or some of the areas for potential improvement, maybe in a particular category, and you come up with ways to address that. And we believe as we go through this that we've done exactly that. Can we go ahead? I know we're running short on time, so I'll be brief as possible. This is just a quick video on how a pigging operation, what it looks like when the use of a pigging ball valve, right, as opposed to the barrel style launcher. So there's the valve. I'll explain the actual features of this. The valve is now isolated. We're bleeding in this case, a liquid out of the bottom of the valve. There's a secondary safety valve to bleed whatever may be left. Closure opens, pig goes in. Closure is closed. Valve is cycled. Pig goes down through the pipeline, very dirty pipeline. We know nobody on this call is a pipeline that dirty. Catches on the other side. There's a counter valve on the other side that will catch the pig. Same bleed operation happens. Same secondary bleed operation happens, which I'll also explain. Closure's open, swung open, pig comes out, and your pigging operation is complete. So that's what happens with a pig ball valve, as opposed to having to isolate with a different valve, having to open the barrel, load the pig, release the isolation valve, and then have the pig go down. So it's certainly more efficient from an operations standpoint, in that the number of people required to do that is significantly less, right? So what we've done that's a little bit different, a lot of the traditional pigging ball valves that have been in the market for the last few years have utilized a top entry design where the actual closure is on the top of the valve. It has a threaded closure so that you have to climb on top of the valve, undo the closure, do something with the closure. Either it's mounted on a davit or it comes clean from the valve, and then you have to put the pig in, thread the closure back, and then go from there. What Chaoda's done a little bit differently is that we've moved the closure on the side of the valve so that it lines up at torso level, right? So it's a little bit easier access, and we believe the access portion of it kind of helps with the number of operators required to do the pigging operation itself. Go ahead. Another advantage of the style of closure that we have designed is there are no threads. It's not a threaded closure, so it's not susceptible to environmental conditions that may lead to thread corrosion, thread galling, anything like that. So it's more of a traditional style closure. There are guides for the closure so that when it swings out, the closure never leaves the valves. And the actual operation of the closure, as opposed to a threaded multiple turns to get the closure open, we just have a quarter turn style of operator that breaks the locking tabs free so that the closure can get released, somewhat like a bank vault, right? So an airplane door, a jet door, you just crank it a quarter turn and then you pull it out. Go ahead. The closure itself, as I mentioned, runs on guides. It's also a double hinge style, right? So you pull it out and then it hinges on the double hinge, very lightweight. Swings free of the opening itself, and again stays put, never goes anywhere. It's the safest from a pinch point perspective, the safest closure we think that is out there, and certainly because of the fact that the closure never leaves the actual valve itself, and it stays attached together with the style and the weight of the closure. It reduces the amount of operators required to do this. So it could be as few as a one-man operation, certainly no more than a two-man operation. Good. The next thing we've really done, we've tried to focus on, is the safety aspect of it. And so there is the normal cavity bleed that happens when you isolate the valve. But in event that there is some obstruction from some of the cavity pressure or something that keeps it, or even gravity, right, that keeps the body cavity from venting all the way, we have a secondary relief valve system that ensures that the body cavity is completely relieved, and that's via this needle globe style valve that's on the face of the closure itself. So you go through, and you saw it in the video, right? In the video, you saw a quarter turn valve, but it's you bleed the bottom, the cavity, or the side of the valve, depending on whether you're running gas or liquids, and then you do this secondary relief before you can open or close the valve. And it is a safety device, because I'll show you in the next slide, you cannot open the closure unless this particular safety valve has been released, okay? So this safety valve is designed, and the closure is designed so that there's a mechanical pin that is attached to the secondary relief valve, the bleed valve, and it is mechanically located next to the locking tabs on the closure lever itself, so that it is impossible to unlock the closure unless that relief valve is open. So that's a safety feature we've put in there to make sure that there is no chance that somebody can open up the cavity of this ball valve with there still being pressure left in there, okay? So to me, to us, that's a significant safety advancement over some of the traditional pig valves that are on the market, where there are no auxiliary or secondary relieving systems in play or available that they can do that. Go ahead. One of the other ways we've tried to make this valve more efficient is the catcher plate option, right? So our catcher plate, unlike many of the other valves, is integral to the seat ring. It's one of the advantages of that is it does minimize parts within the valve itself, and it also makes reversal easy, right? So if you have a valve in inventory, or let's say CGIS has a valve in inventory that is set up as a launcher, right? That's set up with the catcher plate on the upstream side so that the pig can be inserted and the line pressure will shoot the pig downstream. And it needs to be installed as a receiver, in other words, with the catcher plate on the downstream side so that it will stop the pig when it's coming down the pipeline. You can do that as easily as just disassembling the valve and reversing the seats that, as I mentioned, are integral with the catcher plate. So the seat rings are the same upstream and downstream, whether they have a catcher plate in them or not. So the catcher plate is oriented in such a way that it does not impede the sealing or does not change or alter the geometry of the seat ring itself. So very reversible and transferable. Go ahead. We also offer two different styles of catcher plate. So the traditional for natural gas service is the drilled plate that you see on the left, right? So that's perfectly fine for clean natural gas where there's no sediment, no impediments, nothing to get caught up in the catcher plate itself or impede the flow. In a lot of cases where there are liquids or in our particular market down here where these things are used a lot in oil service, there are paraffins, there is sediment within the oil itself, and it can severely restrict the flow through the traditional gas style plate. So we've developed a liquids plate that has broader or wider flow openings and will allow sediment and that sort of thing, and liquids and paraffins and some of the other things that can obstruct the flow to pass on through the catcher plate itself. And again, as far as the interchangeability goes, if there's a valve in stock, for example, with a gas catcher plate, and you decide you want a liquids plate, that can just as easily be changed out. Just disassemble the valve, take the gas plate with the seat ring out, put the liquids plate with the seat ring in. So easy enough to change. In summary, I told you this would be quick. In summary, Chaoda happens to manufacture this valve up through 20-inch in size, ASME classes 150 through 900, flanged. We can also do this configuration in a metal seated as well, right? So Chaoda has significant metal seated capabilities, and a big part of our ball valve product line is metal seated. These are forged three-piece bodies, again, just like a Trunnion ball valve platform, just like our Trunnion ball valve platform. Easy to access and operate, the easy loader closure, the high flow solids resistant plate. We have API 6D license, and we have our CRN numbers for Canada. So that's a brief overview of the pigging ball valve, the differences, where you might select it, where you might use it, and also some of the features that are all about personnel safety and ease of operation. Braden?
Perfect. Well, thank you so much, Richard, Doug, and Kevin. Great presentation. A lot of good interest, a lot of great questions. We'll try to get to those now. I know we've gone 10 minutes over a lot of time, but we'll stay on and answer any of those questions for you guys. We're going to throw a quick poll question on there as well, just to gauge some interest in the pigging valves versus pigging barrels. So if you have some time and can answer that, we'd love to get your feedback. But like I said, some really good questions. We tried to answer them as we went through, but I know there are some follow-up questions. So the first one, I think maybe to Richard and or Doug there, just regarding the single piston effect seats. When would a single piston effect seat not be considered a self-relieving seat, or is that those terms sort of interchangeable, or what's the difference between those two types of seats?
You can, so I don't want to belabor the difference, because for most manufacturers they are essentially interchangeable. Most people's single piston effect seats are self-relieving seats, but you can design a single piston effect seat that does not self-relieve. It would depend on, like, basically most like for Trunnion ball valves specifically, your piston effect is overcome by body cavity pressure that allows it to basically, that body cavity overpressure backs off the seat that is spring loaded, right? And it kind of, the seat kind of burps, and the body cavity overpressure goes to the line. But you can have a valve that would be designed, maybe, for example, without springs, that would be able to have a single piston effect, unidirectional seal, but would not necessarily relieve in the same way. So, but that is to say, they're not exactly the same thing, but basically all manufacturers treat them like the same thing. And if you have a one-way seat, it is typically a self-relieving seat.
Great, thank you. Another good question that came in that I know is sometimes misunderstood in the industry with regards to installation direction and high pressure end, especially when you have a single piston effect with a double piston effect seat like you would in a DIB2. What is the correct installation? And the question specifically was for pump isolation. The suction valve would be installed with the single piston effect and double piston effect, but the discharge would be the opposite, double piston effect by single piston effect. So a question there, but do you want to speak to that installation direction and the importance there of what you're isolating?
You want to grab that one? That's exactly what you kind of talked about yesterday or the other day.
Yeah, I think for me, and Kev, feel free to jump in here too. But Richard commented on it. When we look at a valve, in particular isolation, we look at it at two states. Where there's the flowing state when the valve is fully open, and then there's the isolation state when the valve is doing its job of isolating. And what we need to look at is where the high pressure end is when that valve is isolating, and what are you isolating. So in terms of a pump, the normal flow when the pump's running is from the pump downstream. But if you're looking at like a if you're pumping uphill or what have you, and you're looking at what you're isolating when that valve is closed and the pump's off, it's actually, you're isolating in the reverse direction. So your high pressure end actually becomes the opposite. And so when we look at installing the valves, especially unidirectional valves or DIB2 valves, you want to make sure that the high pressure end is on the opposite side that you may think based on the flow direction.
Yeah, I think in general, kind of where the rubber hits the road is you want your most secure sealing direction operation seat up against the piece of equipment that you're trying to actually isolate, right? So again, the distinction, like Braden said, the distinction between flowing versus isolating, I think that's the key thing.
Right.
Agreed.
I
There's been
always think about it this way. I don't care what the valve is experiencing when it's open. It's when it's closed that
That's right.
that it matters to think about.
Right.
Yeah.
Right.
You ought to be selecting your valves based on what they do when they're closed.
Exactly. Right.
Yeah.
And that leads to another couple questions around isolation capabilities. So I think, Doug, you saw one in there about what's the isolation class for trunnions and DIB valves.
Yeah, so 6D mandates a bubble tight shutoff, right? So there is no distinction as far as shutoff goes when it's a 6D rated valve. Okay, so yeah, I think
that
Richard did. I'm sorry.
That would be ISO. I think 6D refers to ISO 5208 rate.
5208, correct,
rate,
right?
So rate A for soft-seated valves. Yeah. So that would be a zero leakage test. Now, one of the other follow-up questions was on dirty service, and I think this is something that we run into, especially in Canada and around the oil sands and northern BC and northern Alberta, where unfortunately a lot of our gas and oil coming out of the ground is not as clean as we might see in places like Houston and places like that. And this is a problem that we tend to run into with trunnions, is that technology and as great as it is for clean services and using resilient seats in those applications, and knowing you can get reliable isolation, double DIB isolation, the moment we start to introduce particulate and abrasive medias in our service, we need to now consider the sealing surface. And to get that rate A on most trunnions, you're looking at soft seat designs, which are going to be potentially damaged by that those solids in the line. So unfortunately, we see quite often users taking specifications, looking at AMLs of conventional soft-seated trunnion designs and applying them into difficult applications and not getting that repeatable isolation that they've expected or they've come to expect in more benign services. And so there's that consideration, I guess, that we really have to look at, is what is the application, as Kevin touched on early on in the presentation. What's the application? What are we seeing? And then selecting the right product and seat design for that. Yeah. Okay. Good. All right. A lot of other. Does Osha accept API 6D double block and bleed? Is another question.
No.
That's a no. So OSHA requires 2 valves, and that's the key, sticking point there. So a API 6D defined, double block and bleed capable trunnion ball valve, for example. Hey, look, you can isolate pressure from 2 directions, have positive verification from the drain valve, but that does not meet the OSHA definition because OSHA requires 2 valves.
Yeah, so you can have the OSHA definition satisfy API, but not vice versa.
Okay. Another question here. In a ball valve, if you have DIB1 that has been ported for thermal relief, does it essentially become a DIB2, or is it still DIB1?
It's still a DIB1 because it seals against pressure regardless of the source still. Yeah. So it does, in the sense that it once you've, ported it or put that piping in there, now you've taken care of the body cavity overpressure problem. But the valve is still going to have 2 positive seals against pressure regardless of the source or direction that it comes from.
Yeah, the DIB1, DIB2 is all about the seat configurations, right? So any external porting or any auxiliary equipment that you attach to it, that's it's sort of irrelevant to the seat design, right? So it may change the functionality of the valve, but that's because you've added external, accessories that do that, right? Seat configuration is the same.
Perfect. All right. Maybe moving over quickly to the pigging valve. There's a few questions around size and rating, as well as temperature limit. I think I saw in there. So I know you went over that briefly, but maybe just reiterate what we have there.
Okay.
Really, with the temperature rating of the valve, it comes down to the valve materials that we're using in manufacturing of it.
The normal seat insert on a pig valve is Devlon, right? So it is, and with all of the limitations that Devlon brings from a temperature standpoint, there are, because it's essentially a trunnion ball valve seat, there are options to that, right? You can use peak seats and get a little bit more elevated temperature capability. And as I mentioned, you can use metal seats, which gets you significantly higher temperature capability, right? So yeah, it's just, it really, the temperature capability is really mandated by, are really dictated by the seat insert materials and the O-ring materials that the valve itself has, all of which are, there's some options.
And to follow that up, I mean, with the temperature rating, we can do the low temperatures that we experience in Alaska or in Western Canada.
Yeah, we used to think we didn't deal with low temperatures here, but apparently.
Yes. Another good question here. Saw a couple times. What pressure does a double isolation seat cavity pressure relieve at or lift the seat at? I think.
I was just typing on that. So when you're talking about relieving body cavity overpressure, whether you're talking about a self-relieving seat or a piping set, typically, so for the self-relieving seated valves, either a DIB2, for example, or a self-relieving trunnion with two one-way seats, it will relieve the differential pressure. So if you've got a line with 200 psi in it and your body cavity builds up to 205 psi, it's going to relieve that 5 psi of differential pressure through the self-relieving seat. When you talk about the accessories, as Doug put it, the kind of the body cavity relief piping, usually those will have a set valve that's set to crack at a specific pressure. That's also true for like a vent valve that just vents to atmosphere, and they will set that at a pressure appropriate for the pressure class of the valve. So for example, for a class 150 valve, they may set it to about 300 psi.
Perfect.
And it will just crack at 300 psi until the body cavity pressure gets back under 300 psi.
Equalizes, right?
Yeah.
Perfect. Just a couple of ones that we've answered already. The pig valve can handle only clean pigs or instrument smart pigs. So Richard did mention that really just the valve is designed for cleaning pigs. With smart pigs are normally longer and would need the more conventional launcher and receiver.
That's true.
There
apparently is work underway for developing smart pigs in a smaller, more spherical format, as opposed to the long smart pigs that we're accustomed to seeing, right? So hopefully one day in the not too distant future, we'll be able to accommodate some measure of smart pigs in a pig valve.
Another question on the pigging valve, just on how does the isolation work? Each side only single isolation, or is it a
double? It's a double block and bleed configuration, basically. Okay. So, it again at at the point of isolation, it's a double block and bleed trunnion ball valve. That's what it is. Okay. Now, obviously, the body is a little bit bigger because it has to accommodate the closure, etc. But at the point of isolation, it's a double block and bleed trunnion ball valve.
Okay, in case of seating failure in CGIS valves, is there a means of an emergency injection sealant as a temporary sealing mechanism until primary seats can be restored?
Yes.
That's a positive. Yep.
Yeah. Okay.
And in addition to the seat, the stem as well.
Okay. And that's accomplished through the injection ports.
Yes.
Yeah. Okay.
Exactly.
Okay. Another question here popped up. If we close a DIB2 valve when line is pressurized, then we bleed up and down for safety. Should we open the ball or at least open the drain before we remove the valve? I guess that would be for removing the valve from the pipeline.
I would say yes.
Yeah, I would say
Want to
yes.
vet that valve.
Yeah. You want to do everything you can to make sure that there is no residual pressure in the valve before you start breaking the integrity of the pipeline.
Excellent. Think trying to read through here. I think we probably answered most of them. If there's, I guess we're coming up on an hour and a half, so half an hour over. I think it's probably a good time to cut it off there. Again, I really appreciate everybody's time that stuck around. We did record this, and Sam will be following up with everybody that signed up with a thank you and some collateral to include in the email there. So again, really appreciate it. Again, to Richard, Kevin, and Doug, thanks a lot for your time. Great presentation, a lot of good knowledge there. And if anybody else has any other questions, feel free to reach out to any one of those three or myself, Braden Waters. The emails for our three panelists are on the presentation there right now. Otherwise, everybody have a safe rest of the week, and we will hopefully catch you next time.
Thanks, guys.
Thanks, everyone.
Absolutely. Thank you, everyone.
Thanks, everyone.